Okay, welcome back to Calculus. In section 8.3, we're going to take a look at a couple of applications of the definite integral to problems in physics. And in particular, in the first part of this section, we're going to take a look at something called hydrostatic force and hydrostatic pressure. Okay, so the outlines for today, I want to talk about the definitions and the units for the quantities that we're going to be using. Those quantities are going to be densities, both mass and weight densities. I want to talk about hydrostatic force and hydrostatic pressure. I'll define them and say what units we're going to use. Our local estimate will be based on something called Pascal's principle. So we'll quickly take a look at Pascal's principle. In the module, you probably noticed that there's an external YouTube video that I linked to that has a really nice explanation of some more of the physics, more detail than I'm going to go into here, but I hope you'll at least skim through that video. It's got some really nice illustrations and things to think about there. So then we're going to take a look at the constant depth case. That's going to be our local estimates using Pascal's principle for these hydrostatic forces and pressures, and then we'll do a couple of examples where the depth isn't constant, and that's where our integral is going to have to come in. All right, so that's how we're going to proceed. I'm going to just go ahead and lay out these book notation. This is the notation for all these quantities in the book in this table. I won't spend a ton of time on this slide because you can kind of stop the video and look at this stuff. But these are the notations and the units that we're going to use on these quantities. So we'll just kind of talk about them one at a time. So the mass density of our objects, the book is always denoting by the Greek letter rho. So mass density is denoted by rho. And in the SI unit systems, it would be denoted by kilograms, or its units would be kilograms per cubic meter. In the US units, it would be slugs per cubic foot, okay, because the unit of mass in the US system is a slug. Okay, the acceleration of gravity, you have to multiply by mass densities to get weight densities. It's denoted by little g. Its units are meters per second squared or feet per second squared, depending on the unit system. The weight density of an object, which is gravity times its mass density, the book denotes it by the lowercase letter delta. Its units would be newtons per cubic meter or pounds per cubic feet. Okay. The depth of our object, the book denotes it by D, D for depth. If you're in SI systems, it's measured in meters. In the US system, it's measured in feet. Area, capital A, meters squared, feet squared, depending on the unit system. Our forces, capital F, newtons or pounds, depending on the system. And then pressure, if you're not used to the definition of pressure, I'll define it below, or maybe I can just write it right here. Pressure, by definition, is force per unit area. It's force per unit area. So in the units that we're going to be working in here, that would be newtons per square meter, which has an alias. It's also called a Pascal, or pounds per square foot. Okay, and in chemistry and lab sciences, typically you use different things. If I don't, it's been a long time since I've been in these courses, but I think people use kilopascals, yeah, because these units are sort of big or small rather, or pounds per square inch. You're probably more used to that if you've ever pumped up a bike tire or something like that. You pump it up to a certain psi. That psi stands for pounds per square inch. It's also a unit of pressure, but they're just measuring distance in inches instead of feet. But for us here, for the purposes of this section and in our class, we're going to stick with these units. Okay, so just kind of like in the work problems, if distances are given in centimeters or something, conversions have to be done before these formulas I'm going to derive are applicable. Okay, so I work in meters and newtons, feet and pounds, and so on. Cool. So that's a little bit of our units. You can reverse the video, come back to this as much as you like to check it out. So here is the kind of physics problem I want to talk about. If you take some flat two-dimensional surface, and when a mathematician says a two-dimensional surface, she or he means exactly that, no thickness. So think of like a piece of cardboard or something like that, but we're ignoring the thickness to it. So we only think of it as two-dimensional. So it has a length, it has a width, it has no thickness, it has no volume. So you take a two-dimensional surface with a given area A, and you submerge it in some fluid so that all points on the surface are at the same depth. Okay, this is all points of the surface are at a constant depth D. You can see in my picture down here, I've got a surface of a fluid drawn there, right? And then I'm taking my two-dimensional surface. You're looking at its end view here. If I put some depth in the picture, this surface is some surface like that, but just think of this picture, we're just looking at it straight on, right? So when you look at a piece of cardboard from the side at eye level, you just see its edge. And that edge, I'm treating it like it has zero thickness. But all points on this surface are at the same depth, okay? So the weight of the fluid exerts a force on that surface. That's the kind of physical principle. The weight of the fluid, if you've ever been in a swimming pool or if you're a scuba diver, as you descend in the water, you feel this force. Yeah, because that fluid has weight. And as you go deeper and deeper in the fluid, there's more and more weight pushing on you, and you can feel it. You can feel that force. That force is called the hydrostatic force. So hydro because of fluid, static because nothing is moving in time, and it's a force, it's a weight. Okay, and how would we calculate that force? Well, I've got it already written out here for you. Let me just kind of walk you through it. If I took the weight density of the fluid and I multiplied it by the acceleration of gravity, well, that give, sorry, if I take the, let me back up. If I take the mass density of the fluid and I multiply it by the acceleration of gravity, well, that gives me the weight density of the fluid. I've written some units over here. So the book is calling that delta. Go back to the slide if you need to. That would be in like newtons per cubic meter or pounds per cubic feet, depending on the unit system, right? So I'm taking how much the fluid weighs per cubic unit, and then I'm just multiplying that by the volume. The volume above this plate, again, for me, it's kind of easier to imagine if you draw this picture with some depth in it, right? The plate has area A, and there's a column of water. That's a scuba diving term, if you like. There's a column of water above that plate because it's at constant depth. And what's the volume of that column of water? Well, the volume of that column of water is the depth times the area. It's just a big box of water, right? So you take the area of the base times the depth. So the depth is in meters, the area is in square meters, so the volume is in cubic meters, or if you're using US system, cubic feet. And you can check that the units on this, well, newtons per cubic meter times cubic meters is newtons, or pounds per cubic foot times cubic feet is pounds. So this is in the units of force. This is the force. Okay, so you take the weight density of the fluid times the depth of the fluid times the area of the surface, and that gives you the force in newtons or in pounds, depending on your unit system. We just said this above, but pressure is by definition force per unit area. So you just take that force equation above there and divide it by area. So the pressure is just the weight density times the depth. Okay, throughout this entire section, we are going to use the weight density of water is 9,800 newtons per cubic meter. So I'm just taking 1,000 kilograms per cubic meter and multiplying it by the acceleration of gravity. That's our weight density of water. In the US system, I'm not sure if this is actually scientifically accurate. I think it's close, but for computational purposes everywhere, we're going to use the weight density of water as 62.5 pounds per cubic foot. Okay. So some just setting it up. What do I mean by the hydrostatic force for a surface of area A at constant depth? I mean the weight of the fluid above that, the column of water, as scuba divers say, above the surface. What do I mean by the hydrostatic pressure? I mean the force per unit area. Let's talk about this Pascal's principle. Pascal's principle says that at a given depth, that fluid pressure is the constant from all directions. Fluid pressure is the same in all directions, is what Pascal's principle says. So in my little picture over here on the left, I've just taken my surface A. Remember, we're just looking at an end-on view of it, and I'm just putting it in the water at different positions. And then what I've marked on that is a point always at the same constant depth. Those 3 points A, B, and C are at the same depth. So because pressure only depends on the depth and the density, the pressure at those points is always the same, and it's the same in from all directions. So the pressure, and hence the force, is the same at those points A, B, and C. It doesn't matter how the surface is oriented, is what my point is. Okay, because their depths are equal and the areas are equal. Okay, so the pressure couldn't vary. So I would encourage you to watch that video. Watch that video in the Canvas module where the author of the video, sorry, the producer of the video talks a little bit more in detail about how to think about this Pascal's principle. It's pretty good. It's pretty good stuff. Okay, so we're going to use this to make our local estimates. Let's start with a non-calculus problem. Let me emphasize that here, that example one has no calculus in it. Okay, so what am I doing? I'm taking a 3 foot by 4 foot plate. So that's my two-dimensional surface. Think of it as like a sheet of plywood with no thickness. And I'm going to submerge it in water. Submerging it in water, so we know what the densities of those things are. And I'm doing it horizontally, meaning that all points at it are at a constant depth, and in particular, that constant depth is 8 feet. So check out my picture down here. Here's my surface. Looking at it as an end-on view, every point on that surface is 8 feet below the water. We wrote above that the weight density of water is 62.5 pounds per cubic foot. That's our assumption. So what do I want to do? I want to calculate the force on the plate. I want to calculate the pressure on the plate. So this isn't a calculus problem because the depth is constant. So we wrote above that force is weight density times depth times area. Okay, so you take 62.5 pounds per cubic foot times 8 feet of depth times 12 feet of area, 12 square feet of area. You can verify that's 6,000 pounds. I hope I did my arithmetic correctly. So 6,000 pounds of pressure on that object. Okay, you can check out in the video, but I'm ignoring all kinds of things here about buoyancy and so on. I'm just sort of only thinking about this one quantity, the fluid pressure. So don't worry about like, well, what is suspending the plate? Why isn't it sinking and so on? Those are other considerations that we're not. So just if you had this plate, if it has basically the exact same density of water and you hold everything else constant, then it would just float there. And this would be the pressure on it. So it's, you kind of have to think about its buoyancy is matching this force to keep it floating there. But we're ignoring everything there. We're just talking about the force on the plate. Okay, so simplified physics here. What's pressure? Pressure is force per unit area. So you just take the force calculation above and you divide it by the area. So 500 pounds per square foot. 500 pounds per square foot of pressure on that surface. Okay, not a calculus problem because the depth is constant. You can guess what example 2 is going to be then. Let's take that same plate, but this time the language I'm going to use is I'm going to submerge it vertically. So I'm going to just use pictures to say what I mean by that, but I'm taking my 4 foot by 3 foot rectangular surface plate, and I'm orienting it straight up and down in the water here so that its top edge is 4 feet below the surface of the water. And I would like to ask the same 2 questions. What is the hydrostatic force and pressure on that plate? And this is a calculus problem because, well, the depth is not constant on that plate, right? Points like, say, right here on the plate are experiencing less force and less pressure because their depth is not as much as, say, points down here. The force and pressure at points down there is going to be more. So the depth is not a constant. So I have to somehow account for that. So we're going to make a local estimate. Let's coordinatize the problem. I'm going to put a coordinate system in this problem. And instead of pre-drawing it out, I decided to do it along here with you. So I'm going to put a number line in the problem that's a vertical line measured straight from the top. And this is a choice of mine. We're going to talk some more detail about this tomorrow, but I'm going to make the choice that the x coordinate, I'm going to call the values on my number line x. I'm going to say that the x coordinate is 0 is the surface level of the fluid. Okay, so I've chosen that coordinate system. So therefore, the top edge of my plate then is at x equals 4, right? The bottom edge of my plate must be at x equals 8. Because it's 4 more feet down from the top edge. Of course, I didn't draw this picture to scale. So the 4 feet, the picture is not drawn to scale, it's schematic, right? So those are the extreme x values. So if I pick a value of x between 4 and 8, I can imagine a cross section at that x value. And so what I'm going to do is I'm going to give myself a little rectangle draw another value here, call its thickness delta x, okay? And the idea is that if delta x is small, then I can assume that all points in that little shaded rectangle that I just made are at the same depth. So that's kind of my idea. Delta x is small. All points in that rectangle are at the same depth. Of course, that's not true. I should say they're approximately at the same depth, but that's my local estimate, okay? So if I were going to try to estimate the force on that rectangle, right, I can do it just like we did the above problem. I can do it just like we did the above problem because I'm just assuming that this rectangle is really like infinitely thin, that it's just a surface. And remember, Pascal's principle says that it doesn't matter which orientation. So if I took this rectangle and sort of flipped it so that we looked at an end-on view, and I think of that thing as always being at the constant depth, then that's how I'm going to make my local estimate for this force. Okay, so the force is the weight density of the fluid. I'm working in feet here, so I've got that constant, right? It's 62.5 pounds per cubic foot. Maybe it's useful for me to write that here, pounds per cubic foot. What is the depth? Well, I'm assuming that all points on that rectangle are at a depth x, right? So that's x feet. What is the area of that rectangle? Well, that rectangle is 3 feet wide and delta x tall in the picture. So the area of it would be 3 delta x. That would be in feet squared, right? So I'm assuming that all points on that rectangle are at depth x. The area of the rectangle is 3 delta x. So that's my local estimate. So if I added those things up, the force should be approximately the sum of that stuff. It should be the sum of 62.5 times x times 3 times delta x. And what does x range between? It ranges between 4 and 8. So that gives me the ability to write down the integral. The actual force is therefore the integral from 4 to 8. Remember, those are my extreme x values. This region is occupied in my coordinate system from x equals 4 to x equals 8. And what am I integrating? Well, I'm integrating 62.5 times 3 times x dx. I'm going to leave that unsimplified. I'm just rearranging the terms because I like the dx to be at the end. Yeah, so I have to integrate that thing like that, right? 63.5 times x times dx. All right, so now we actually have to carry out that integral. I'm looking around for a piece of paper on my desk because I thought that I had already carried out this calculation, but I guess I didn't, so we're going to have to do it together here. So what do we have to do? We have to, let's just drag that constant out front. So I've got 62.5 times 3, and then I'm just integrating from 4 to 8 of x dx. Okay, well, the antiderivative of x dx is 1/2 x squared. I'm going to save all the arithmetic for the end here because I don't have it worked out, and I'm going to have to grab a calculator to make this go faster. But I'm going to divide by 2 and add 1 to my exponent, and then I have to integrate that from 4 to 8, right? So I can write down what we're going to get here. We're going to get 62.5 times 3 over 2. Evaluated 8, that's 64. Evaluated 4, that's 16. All right, so now we have to do that calculation. I'm just going to get out my calculator here and do it along with you. So 62.5 times 3 divided by 2 times the quantity 64 minus 16. You probably beat me to the punch, but I'm getting 4,500. 4,500, and that's 4,500 what? That's 4,500 pounds. Yeah, 4,500 pounds. Okay, so that's how we can compute that calculation. What's the pressure? Well, pressure is force per unit area. So we need to take that 4,500 pounds and divide it by the area of the plate. So we have to take 4,500 and divide it by 12. It's 375. And what would the units be? Well, pounds per square foot. So the force on our vertical plate is 4,500 pounds. The pressure on it is 375 pounds per square foot. Nice. Okay, cool. So let's do a second example. You can pause the video and let that stuff soak in. Let's do a second example. It's example 3 because the first one didn't have any calculus in it. So this time I'm going to take a triangular plate and submerge it in water as shown. So when I say that, it's implicit. I should write this more carefully here, but the top edge of this triangle is parallel to the surface of the fluid. So it's submerged like that. The top edge is 1 meter below the surface of the fluid. The triangle is 5 meters long and 3 meters tall, and it's a right triangle. I should have indicated that, but it's a right triangle. Okay, so it has a 90-degree angle. And I want to do the same thing. I want to find the force, I want to find the pressure. Okay, so we've got the idea out there. I need to kind of make a local estimate. I need to coordinatize this problem, right? So I need to put a number line in the problem. And there's different ways to do that. Here, I'm going to start by doing it over here. I'm going to write right through my labels here. But let's say I put my number line over here vertically. So this is my sort of, I'm going to just call the variable x again. And I like the surface of the fluid to be at x equals 0. Okay, so if I do that, well, then the top edge of this thing is at x equals 1 in my coordinate system because the fluid is 1 meter below the surface. This lowest point, that vertex of the triangle, well, it's 3 more meters down, so that's x equals 4. Right, so that's x equals 4 meters down there. So those are going to be our limits of integration when we're done. We need to make a local estimate. We need to choose an x value between 1 and 4 and look at a slice. Okay, unlike the previous example, you can see that the length of this slice is going to depend on x, right? If I picked x a little less deep, that cross section is longer. If I picked x a little deeper, it's shorter. Okay, so we have to work out. Let me draw my rectangle again. So let me thicken this up a little bit. Same kind of idea as before, that I'm going to be assuming that all points in this rectangle are at the same depth, x, right? But this rectangle's width, unlike before, depends on x. So it's the width of a cross section at x, where x is between 1 and 4. And we need to figure out, well, what is that w of x? Because I can make the local estimate in terms of w of x right now. Our local estimate, and I mean the local estimate for the force, by the same principle as above. I'm going a little bit faster here, but you can stop it and soak this in. I have to take the fluid, the weight density of the fluid. I'm working in the SI units here, so I'm going to take 9,800, that's newtons per cubic meter, if you want me to write the units. And I have to multiply it by the depth of my rectangle. Well, the depth of my rectangle is x meters in my local estimate, and I have to multiply that by the area of the rectangle, where the area of the rectangle here is the width, w of x, times delta x, the thickness of it. Okay, so unlike the previous problem though, w of x is not a constant. In the case where the shape was a rectangle, that width was the same all the way down. If I recall correctly, in the rectangle above, it was 3, but now it varies. So how do we find out what this wx is? Well, I'm going to use similar triangles to do that. So if I just sort of chose a bold pen color here to highlight the triangles I'm looking at, there's this one I'm coloring pink, and then the original one. And those are similar because they all have the same angles, right? They're right triangles and they share a common angle, so all 3 angles are the same. So by similar triangle principles, ratios of their side lengths are the same. So what I need to do is take the ratio of, say, this vertical leg of the pink triangle to W, and I can set that equal to the ratio of 3 and 5, right, by similar triangles. How long is this vertical length? We've talked about this a lot in this class. Look, I've got a number line. The lowest point is x equals 4, and the other point is x, and I can see that 4 is bigger than x. So that side length, if I wrote it in there in the same pink pen, that side length is 4 minus x, right? So by similar triangles, I can write that 4 minus x, its ratio to this w of x, has to be the same as the ratio of 3 to 5. Okay, so if you solve that for w of x, what do you get? Just kind of, I don't know if you like to think about it as cross multiplying, but w of x is 5/3 the quantity 4 minus x. Okay, so that's what goes into my local estimate over here. The Riemann sum would be adding all of that stuff up. I'm not even going to write it because this is enough information so I can write the integral for the force. The force is the integral, we already said, from 1 to 4 in our coordinate system. And then what am I taking? 9,800 times x times the w of x we just found, 5/3 times 4 minus x dx. All right, and clean that up a little bit. The constants come out front. That's 9,800 times 5/3. We can do the arithmetic in a second, times the integral from 1 to 4. And then I'm multiplying x by 4 minus x. I'm going to write one more expression here. That's 9,800 times 5/3, integral from 1 to 4 of just 4x minus x squared. And that integral is not difficult. I'm going to skip the computation of it to save time. Keep this video a little bit shorter, but I hope you'll work it out. Use all those constants and everything. You should get 147,000. And in this unit system, that's 147,000 newtons. Okay, so that's the force on our triangular plate. What's the pressure? Pressure is force per unit area. So I have to take 147,000 and divide it by the area of this triangle. Sorry for the scrolling. The area of a triangle is 1/2 its height times its base. So in this particular case, I'm just going to write it out in that form. 1/2 the height times the length of the base. That's 1/2 of 15. And I'll let you check my math that comes out to be 19,600. That's 19,600 watts. Well, it's newtons per square meter. Or if you prefer, you can call that a Pascal. Okay. So there's a computation showing how to proceed to set up the local estimate when the width of the object is not a constant. All right. Well, I'm going to keep this a little bit short, but I want to make one more comment. One more comment before we end this video about choosing the coordinate system. All right. Because one of the things that makes this kind of a little bit subtle to learn is that is a choice. No one tells you. So I'm just going to scroll back. You can pause if you're not done looking at it, but I'm going to scroll back. Nobody told me to do this, to let x equals 0 be the surface of the fluid so that I wrote that number line down and I kept track of everything in that. That was my choice. And you can make other choices. You can make other choices. Let me choose a distinct color here. Let me pick, not blue, I don't know, red. Here's another coordinate system. So let me draw another line that's supposed to be nice and straight. There we go. Right? I think in this coordinate system, I'm going to call the variable y, just so we don't get confused. And maybe you want y equal to 0 to be the top edge of the plate. You can choose that. Okay, well, if y equals 0 is the top edge of the plate, then that bottom corner is at y equals 3. Right? In this coordinate system, the surface of the fluid would be at y equals -1. It's okay. I personally like the surface of the fluid to be at x equals 0 because then the depth is x. But you can proceed this way. If we take our local estimate here at this y value, uh, uh, same thing, delta y is delta x, it's the thickness. But what we would have to do is work out, well, like, what is the length of that w in terms of this y coordinate system? Okay, what is the length of that w in terms of this y coordinate system? So I didn't really leave myself much room to do this, and I don't, maybe, here's what I can do. This is going to be a little messy for a second, but I'm just going to copy this picture. It's going to be a little bit more than what I want, but we can clean it up when we get down here. Let's go down here to where we have some room. Okay, so I'm trying to recapitulate the problem in this new coordinate system. Let me get rid of this noise for you here, so it's a little bit easier to look at. Okay, so what we have to kind of focus on now is like, well, what is W of Y? How is this width depending on the Y variable? So by similar triangles, we have to, again, look at this edge over here, but that vertical leg over there, its length is now 3 minus y. So we would have to write something like, well, 3 minus y is to w of y, again, as 3 is to 5. So solve that for w of y, and you get 5/3 times the quantity 3 minus y. Okay, so that's your width. And then the same exact principle, the force is the integral of density, weight density, 9,800, times the depth. But let's be careful here. In this coordinate system, the depth is not y, right? Can you see? The depth is y take away -1. That's the length of that thing. Y plus 1 is the depth. So I have to adjust for that, y plus 1. And then my area is 5/3 times 3 minus y dy. And then I'm going to integrate in this coordinate system from 0 to 3. All right, this 0 down here is a bonus, right? It usually makes the computation a little easier. So I think if I zoom out a little bit, you can see both integrals. Maybe not. I had to zoom out pretty far. But notice how different they look, right? This is integral from 0 to 4 of 9,800 times x times 5/3, 4 minus x. This one's the integral from 0 to 3. Completely different integrand. But I'm going to leave it to you to check. If you go through all the calculations, you're going to get exactly the same number. You should get the same number because the force on this thing shouldn't depend on how we coordinatize it. So you're still going to get 147,000 newtons. So I wanted to kind of end this video with that demonstration of choosing a new coordinate system, just to point out that, there is no one and only one coordinate system to do a problem. So sort of how you coordinatize it, how you keep track of the measurements, depth in this particular case, is going to influence what you write down in terms of the integral. And it can make the computation easier, it can make the computation harder. So sort of choosing a coordinate system that facilitates nice computations, it's a little bit of an art form. You get better at it with experience. Generically speaking, I like to do this like I prefer to have the surface of the fluid be the x equals 0, the coordinate being 0, because then when I pick an x coordinate, that is its depth. But sometimes, you might want to adjust that. The surface of the fluid was at -1. What did that buy me? That bought me a limit of integration equal to 0. Sometimes the shape of the region will influence it. Here, the triangle sort of didn't care. In tomorrow's lecture, we're going to look at some circular things, and there I will have sort of a very specific suggestion of where to put your origin, where to measure your distances from. Okay, I hope that was useful. Thanks for listening.